All right, this method here is going to be using second order differential equations, or solving rather, second order differential equations using reduction of order. So we're going to be looking at second order differential equations and specifically homogeneous. And we know that there has to be some linear combination between y1 and y2. Where y1 and y2 are linearly independent solutions on the same interval. Now, reduction of order says that there has to be some type of relationship between y1 and y2, or that if you divide them, it is not a constant. Well, if that's the case, if you divide these two functions and you don't have a constant, then they must be equal to a function of some kind. Or we say that y2 must be equal to some function times y1. And then we can try to figure out what that function is by plugging it into the differential equation. And then we have both pieces. Now, in order to use reduction of order method, you do have to know one of the two solutions. And sometimes you know that, sometimes you don't. So this is just one of many different ways that you could use to approach. So if I know that one of my solutions to my differential equation is e to the x, and I have this second order differential equation, then let's use this method to try to figure out the second one. So if I know that y2 equals some function of u times y1, or times e to the x. Well, then the first derivative, I would need to use product rule to find that. And then the second derivative, when I bring that together, I have u double prime e to the x. I have 2u prime e to the x, and then I have u e to the x. All right, now I want to plug that in to my second order differential equation and try to figure out if I can find what u is. So if I have y2 double prime minus y, what ends up happening when I make that subtraction is I'm just left with these pieces, because if I have this and I subtract out here, then I'm going to have that this is 0, or that e to the x u double prime plus 2u prime gives me 0. Well, e to the x is never equal to 0. So I know that the second derivative of a function plus 2 times the first derivative of the function must give me 0. Now here we have to use a second type of substitution. So I'm going to say, let's let u prime be equal to w. Well, then u double prime equals w prime. And so I have w prime plus 2w equals 1. I reduced my differential order, if you will, by 1. And now this is a first order linear differential equation. What ends up happening is I have my mu is e to the integral of 2 dx. So our mu is e to the 2x. Okay, so let's go through and look at this. So I would then have the derivative of whatever this w function is times e to the 2x has to give me 0. And if I integrate both sides, I get that this has to be some constant over here. And so w must be equal to that constant times e to the negative 2x. But remember, that's u prime. So if I say, okay, well then u prime is then equal to this piece, then u must be equal to, maybe we say negative 1/2 c e to the negative 2x plus like some other function, or maybe I just call this even c1 and c2. Just, it doesn't really matter. They're just constants here. And then up here, my whole big function that I'm trying to find, I need to then multiply that. I'm going to say y is u times that other function. And so you will be able to see, I'm just going to say this is some constant e to the negative x plus some other constant e to the x. And then that's going to be my solution. Now, I'm going to tell you that there's a faster way, okay? That you don't have to go through this whole entire process every single time. The book does go through and show you this process and why it's all the way that it is. U is always going to be like this integral. And we're always going to be able to find our y2 based on our y1 using this equation here. And for my course, I would give this to you. So I would be like, here's y1, here is your second order differential equation. Here, I want you to use reduction order using this formula. Okay, so this would be something that would be given to you on a quiz or an exam. And so let's just use that here on example 2. You do have to put your differential equation in standard form. So I'm going to divide everything by x squared. And this is now going to be my p of x that I use. So I say y2 must be equal to y1 times big integral e to the negative, here px is negative, and then I'm going to put that all over x squared squared. And I do have like a double integral situation. If you think back to y, like I had that reduction of order here where I had to integrate within the w piece, right? And then I also had to integrate again here. So I have to do that double integration in this formula as well. All right, so here we have some positives. And now one thing that students tend to do is they try to bring this inside. It does not. That y1 stays outside. Okay, this is helping us figure out what function am I multiplying by y1 to get my y2. Okay, so this is going to be e to the 3 natural log of x all over x to the 4th. If I use the power rule and do some simplifying, I get x cubed over x to the 4th, or that I'm integrating 1 over x dx, and I get x squared times the natural log of x. You can have plus c there if you want to. Things kind of all just end up canceling out. But if you notice, this is actually a problem that we did before where I was like, hey, verify that these are the solutions. It came back up. Whereas if I gave you one solution here, you could find that second solution using this formula. And eventually, actually next time, we are going to be able to find solutions without any given piece of our equation here. So we're kind of just starting to piece some things together to find out how to figure out what our solution curves of these differential equations would look like. And this is how you would do it if you wanted to use this reduction of order method.